Swayam Prabha. Digital India. Educated India.
Good morning and welcome to this the lecture number 33 of the course Stochastic Hydrology. Over the last few lectures we have been discussing about the principal component analysis, multiple regression and so on, where essentially we want to develop a relationship between the dependent variable y and several independent variables x1, x2, etc., xp. And in the previous lecture, in the last lecture, we discussed the principal component analysis, which has the advantage that it will reduce the size of the problem. Also, it will account for the correlations among the independent variables. And what do I mean by accounting for? Let us say x1, x2, x3, etc., they are mutually correlated, and that leads to what is called as multicollinearity in a multiple linear regression, and therefore, you need to have variables which are not correlated with each other. By carrying out the principal component analysis, this is what you achieve. The original set of x1, x2, etc., up to xp, the p independent variables, you convert into a new set of components p1, p2, p3, etc., pp, p components you derive, and these new components, recall that these components are linear transformations of the original set of variables, and these are uncorrelated. And we also know how much of the variance in the dependent variable is explained by each of these principal components, and based on that we can decide how many of the principal components we would like to retain in the regression. So, let us say you had 10 variables, and then out of 10 variables you may just so 10 variables will lead to 10 principal components, essentially 10 eigenvectors, and then out of these 10 variables, 10 principal components, you may want to retain only 6 or only 3, as we discussed in the previous lecture. So, principal component analysis achieves two things for us. One is that the size of the problem can be reduced. Instead of dealing with 10 variables each with 50 years of data and so on, you may now deal with only 3 variables. So, the size of the problem is reduced, and the correlations among the independent variables that you had originally x1, x2, etc., xp, the 10 variables that we considered in the example, those correlations are removed when we do the transformation. So, this is what we discussed in the previous class. I will just go through that what we did. So, the original variables, and then we use the principal components on the regression analysis. So, instead of doing the regression on the original observed variables, we do the regression on the principal components. So, the original variables are first standardized. By standardize, you now know that we deduct the mean and divide by the standard deviation, and that is how we get the transformed variables. So, this defines the vector x, the matrix x, where you have p variables and then n values associated with each of them. So, the size of x is n by p, n variables, n observations along the n rows, and then p stations along the you will have p columns associated, one associated with each of the variable. So, this is n by p. Now, this is a matrix consisting of the eigenvectors or the principal components. So, you will have the size p by p. So, if you have p stations, remember you get the principal components based on the covariance matrix, and the covariance matrix will be of the size p by p, and you will get the matrix A, which is of size p by p, and that is how you get this is n by p and this is p by p. So, you will get this as n by p. Now, this is the transformed data. From the original data, using the principal components, you transform the data into z. We now develop the regression relationship between the dependent variable y and the transform data z by using the parameters b. Y is dependent variable. So, this is a single variable, it has n observations and therefore, it is a vector n by 1 and this is n by p and this is p by 1. You have b as a vector of parameters beta 1, beta 2 etcetera, beta p. There are p terms. So, beta p. So, this is n by p, this is p by 1 and that is how you get y as n by 1. So, this is how we regress and then we have also seen the expression for b, which is essentially the same as what we did in our multiple linear regression, where we regress the original variables x directly, not even transformation. We used directly the x variables and then regressed y with x. So, this is what we covered in the previous lecture. So, we do the principal component analysis, choose those principal components which explain most of the variance and then based on those principal components we do the regression. This is what we call as regression on principal components. We also saw a example of 10 variables, that means there were 10 rainfall stations and then you are estimating the yield or the runoff at a particular location as a function of all these 10 variables, rainfall in 10 stations in the watershed. And in that particular example, if you recall, what we saw is that if you put all the 10 variables in their original form, that means y regressed upon x 1, x 2 etcetera x 10, you got certain r square value, which is essentially the measure of goodness of the regression relationship. However, the x 1, x 2 etcetera may be correlated. So, you would like to remove the correlations and fit another regression relationship based on the principal components. So, which we did, we used 6 principal components and when we did the principal component analysis, we saw that 95% of the variance is explained by these 6 principal components and then developed a regression relationship. Then we reduced the number of principal components to 3, where 85% of the variance was explained, which means essentially as you reduce the number of components, you are sacrificing some information content. And when you reduce it to 3, you could explain only 85% of the variance. But the interesting point there is, when you reduce the 3 principal components, the coefficients of the first 3 principal components remain the same as that was used earlier. Now, this is an interesting feature of regression using principal components. This we have seen in the previous lecture. Now, we will take this analysis further, this discussion further and see where we get situations in hydrology where you have to deal with simultaneous behavior of 2 or more variables and you are interested in generation of data on 2 or 3 or more variables. And that is what leads us to multivariate stochastic models. So, in today's lecture, we will essentially focus on development of multivariate stochastic models. Let us look at some situations where we encounter these problems in hydrology. Let us say that you have a watershed like this and then there is a stream. You have a stream gauge here at this location. You have observed data at this point. Let us say this is the random variable x. The stream flow at this location, we define it as random variable x. And this x, you have data, observed data like x 1, x 2 etcetera, x n. There are n years of data available. If it is an annual stream flow we are talking about, n years of data is available. We have seen earlier how to generate data on x. Let us say you had 50 years of data and then you want to generate another 100 years of data and many such sequences, not one sequence of 100 years, but several such sequences of 100 years, which you can use for making any decision at this location. Let us say you want to build a reservoir or some such thing, you will base your decision not on one sequence of observed values, but on several sequences of generated values using the observed historical data. We have seen several methods on this, but we will focus on one of the methods, which is if you recall, in one of the earlier lectures we talked about the Markov chain model. So, we said it is a non-stationary AR1 model, autoregressive model with of order 1. This is what we talked, and then we said it is popularly known as the Thomas Fearing model. So, what does the Thomas Fearing model do? It considers the autocorrelations and specifically the lag 1 autocorrelation of the variables. That is, when you have a random variable x, you define rho 1 as the lag 1 autocorrelation. This is the time series now. On this time series you get the lag 1 autocorrelation, and then use these lag 1 autocorrelations to generate x t plus 1 value as a function of x t and lag 1 autocorrelations, and we have seen the expressions for this. Now, the model that we discussed earlier and called as the Thomas Fearing model, which is essentially a non-stationary autoregressive model of order 1. It preserves the mean, the standard deviation and the lag 1 autocorrelations of the data. What do I mean by preserve? When you generate this data, let us say you generate the data for 100 years, next 100 years, the mean of that generated data will be close to the mean of the historical data, observed data. Similarly, the standard deviation will be close to the historical observed data, and the lag 1 correlation is close to the observed data. And we called it as a non-stationary model when we introduced the variation of the mean from time period to time period, and especially for monthly flows we use this kind of models, monthly stream flows we use the kind of model that I discussed earlier, where the mean of June month is different from the mean of July month, different from mean of August month, etc. So, these non-stationarity in the mean as well as non-stationarity in the standard deviation and the lag 1 correlations. The lag 1 correlation between August and July is much different from the lag 1 correlation between March and February, for example. So, these differences in the mean, standard deviations and the lag 1 correlations, they are all incorporated into the Thomas Fearing model. Now, look at a situation where you are not dealing with one stream flow, but you have the same watershed and then you are interested in building a reservoir. Let us say at this location you want to build a reservoir site, and the flows that are coming here are sums of 2 or more stream flows. Let us say you have a stream flow coming here from this point, from this point, from this point and the main stream flow. So, you have 4 stream flows, 1, 2, 3, 4, and the actual flow at this location is sum of 1, 2, 3 and 4, and you want to generate the data for construction of the making decisions on the reservoir capacity here, which means that you would like to generate data on 1, 2, 3 and 4 together. Now, if they are all independent, let us say this is the random variable x 1, this is random variable x 2 and so on, all of these are independent or can be assumed to be independent, or you can afford to ignore the dependence among themselves. Then what do? We can consider each of them as a single time series and generate exactly the way we did earlier. That means, this becomes a time series by itself, and then you generate it using the single site models. Remember, the earlier model that we talked about is a single site model, because we are not considering any other influence on this time series. However, in most hydrologic situations, when we are talking about such problems where 2 or 3 streams are together contributing to a particular location, there will be a significant correlation among x 1, x 2, x 3, x 4 and so on. And therefore, it is important when you are doing the data generation. We are slightly moving away from our multiple linear regression, and then we are now looking at building stochastic models for data generation and data forecasting. Do not get mixed up with what we just discussed in the previous lecture. In previous lecture, our focus was on developing a relationship between the flow at this location and rainfall at several locations. The rainfall was causing the flow, and that is why we built the regression relationship between the flow and the rainfall at various locations. The problem that I am discussing now is much different from what we have discussed in the multiple linear regression. Here we are talking about data generation at this location, that is statistical data generation at a particular location, when it depends on, when it is contributed, the flow is contributed by several streams like this, and these flows are all correlated. So, you cannot afford to ignore the correlations among themselves, among each of these variables when you are considering the flow generation at this location. In the Thomas Fearing model that we discussed earlier, what did we do? We took the serial correlation or the autocorrelation. You were talking about only one time series, and then you were talking about the autocorrelations. Whereas, when we come to problems such as these, where you are talking about simultaneous behavior of several random variables x 1, x 2, x 3, x 4 etcetera, and then you want to incorporate these features of the simultaneous behavior into the data generation model or into the stochastic models, then we need to look at not only the autocorrelations that exist in the series x 1 and in the series x 2, but also the cross correlations between x 1 and x 2. So, your model should be capable of capturing the relationship between x 1 and x 2 and between the values of x 1 itself with respect to time. So, x 1 has a time series, x 2 has a time series etcetera. So, it has its own lag 1 correlations, those should be captured, as well as the dependence on other random variables here x 1, x 2 etcetera. This is what we will do in today's lecture. How do we incorporate the information content arising out of several such random variables, and specifically we will talk about the flows, because these are the kind of problems that we frequently get in hydrology, where there are many streams and then you want to generate data at a particular location looking at cross correlations of these. One thing that I must repeat is that if there are situations where these dependencies can be ignored, or you are reasonably sure that these are all independent or the cross correlations are negligible. In such situations, you can use the single site models, generate data on x 1, data on x 2, x 3, x 4 etcetera, and then add them up to get the data at this location. This is what you would have done if the cross correlations were in fact negligible. However, when we cannot ignore the cross correlations, we must have a mechanism, or we must build models where the cross correlations as well as the autocorrelations are taken into account. Let us see how we do this. So, that leads us to the topic of multivariate stochastic models, and this is what we will discuss today. So, the stochastic models that we discussed earlier for single site, especially the Thomas Fearing type of models, you also have stationary models as well as non-stationary models, as I just explained. When you are dealing with annual flows, for example, they can be stationary models, and when you come to non-stationary models, you are typically dealing with monthly flows or 10 daily flows, 15-day flows, etc., where there is a significant difference or significant variations in the means from one time period to another time period, and that non-stationarity you are incorporating in the models. Then we also have discussed earlier general family of models, autoregressive moving average models. Of course, the Thomas Fearing model that I discussed is one specific case of the AR1 model, autoregressive of order 1. And then in the ARMA models we had talked about Box-Jenkins models, where you express x t as let us say phi 1 into x t minus 1 plus phi 2 into x t minus 2 etcetera plus theta 1 into x epsilon t minus 1, like that. You have autoregressive terms as well as the moving average terms. Just go through the previous lectures and revise this. These were all single site models, in the sense that we were talking about only one time series there. So, x t was a one time series. So, I may put this as, I am sorry, we can write this as x t as a time series. So, with respect to time, you have measured the values on the random variable x, and that is what constitutes the time series. So, we were talking about single site models. So, at one site you have the observed data, and then you are building the models for x t plus 1. Given x t, we are building models on x t plus 1, and this is what we use for long term generation of the data as well as for forecasting of the data. And just to complete our discussion on the previous coverage of the part, we wrote the first order Markov process as x t plus 1 is equal to mu x. Look at this, we had one time series, and from x t you are generating x t plus 1 here. So, this is a stationary model, because we are treating the mu which is the mean as constant. So, it is not changing with respect to t. So, this is constant, and then you have rho 1 which is lag 1 autocorrelation, and this is the random component. So, you have a deterministic component and the random component. Now, when we used epsilon as mean 0 and variance epsilon sigma e square, we wrote the problem in this fashion, that is mu x t plus 1 is equal to mu x, which is the mean of the random variable x. This is lag 1 correlation, and this is a random term now, and this term here makes sure that you get the same variance as the variance in your x, and this is your standard deviation of x. When we use this kind of model, as I mentioned, the generated data will preserve the mean, the standard deviation and the lag 1 correlation, and these are very popularly used in hydrology. When we introduced the non-stationarity, what we did, we made the mu, which is the mean, change from time period to time period. So, you are generating for time period j plus 1, and then you will consider the mean of flows during that period. We generally apply these models for stream flows. So, I keep on using flows, but any random variable these models are applicable. And this is a rho j, which is the serial correlation between jth month and j plus 1th month. What we are doing, you are generating for the j plus 1th month using the information on the jth month, and therefore, you need the correlation between jth month and the j plus 1th month. Let us say July you want to generate based on June data, and therefore, you need the correlation between the flows in June month to the flows in July month, and that is how we generate this, and these are the random components, and typically we use the normal standard normal variates, which is n 0 1. All of this we have discussed earlier, but this is what leads to our discussion today, and that is why I had to revise this. These are single site models. So, as long as you are concerned only of flows at a particular location, you can use any of the single site models that we have discussed earlier. Similarly, in ARMA models, you have AR of p parameters p order, that is phi 1, phi 2 etcetera phi p, and then you have residuals or the MA parameters of q, and then you have a noise term, and this is how we write it in compact form. Now, all of this is past now. So, let us move forward. These are all single site models, where the concern is on data generation, specifically data generation. These models are used for data generation at single site. Now, in the multivariate case, we are interested in data generation of more than one sites. As I said, you are looking at the design of a reservoir at a particular location. Now, the flows may have been contributed by several of these random variables x 1, x 2, x 3, and then therefore, you are interested in generating data at all these locations simultaneously. That means, you have to take into account the dependence of dependence of flows in one site on the flows in another site, and that is how you need to do the data generation. These are called as multi-site data generation models in hydrology, and the broader class is multivariate stochastic models. Now, as I said, if you can assume that these several of these random variables that we are talking about are all independent, then you use the single site models. However, in many situations it so happens that you cannot afford to ignore the cross correlations among these different random variables. So, we now define, let us say we are talking about a situation where we will examine so that we do not miss the points of definitions correctly. Let us say you have sites J and H, these are two different sites. On the site J you have observations. So, this is time. Let us say I have observations 1, 2, 3 etcetera, n number of observations. Similarly, on site H I have observations 1, 2, 3 etcetera up to n, and these are the time steps t is equal to 1, t is equal to 2 etcetera. The time series j on j, that is x j, if we call x j, has its own serial correlations, that is rho k for various k's, lag is equal to 1, lag is equal to 2 etcetera, it has its own autocorrelations. Similarly, the site H has its own autocorrelations. I use autocorrelation and serial correlation analogously. So, both of them mean the same thing. In addition, they will have a cross correlation between this time period and the same time period on H, that is lag 0 cross correlation. They will also have a lag k cross correlation. Let us say this is k time step apart. So, the correlation between the variable on j at time period t with the variable on H at k time steps apart is what is called as lag k cross correlation between variable on j and variable on H, which we denote as x j and x h. So, x j and x h have also have cross correlations, and these cross correlations can be at various lags. What do I mean by that? The flow in j during time period 1, or the other way around we will take flow in H during a particular time period may be influenced by flow on j during k time steps behind. Let us say you were in August here, and then this August flow on the flow in H, August flow on site H may be influenced by, let us say, August, July, June. June flow on site number j, and these dependencies are captured by the cross correlations at a specified lag. In general, when we talk about cross correlations, lag 0 is what is implied. So, we are talking about this as cross correlation. Cross correlation between x j and x h is simply at the same time we take, and then we compute the cross correlation. But we are now introducing a concept of cross correlation at lag k, and when k is equal to 0, this is what we mean, that is a simply cross correlation. So, we use this concept now and introduce in the models the cross correlation at lag k when we are generating the data. So, that is what we mean. Correlation of a random variable between two sites is cross correlation, this is what we have seen. Then lag 0 cross correlation is the cross correlation at 2 points on the same time period, that is actually the cross correlation. That means, you have two sites and you are taking the same time period, then you are computing the cross correlation, that is lag 0. Then lag k cross correlation, which is denoted as R J H k, j is the station, h is the station. So, we are talking about flow in site j and flow in site h, and k is the lag, it is a time lag. So, lag k cross correlation is the correlation between random variable at site j, flow at site j, you understand it as flow at site j, with the random variable at site h, which is the flow at site h, with lag time k. And as I mentioned, lag time is, you have time series here on site j and site h, you have time series, you lag it by k time periods and then compute the cross correlation. That is what is called as the lag k cross correlation. And we use the same expression as we use for cross correlation, except that we now lag the series by k time steps. So, we are talking about the lag k cross correlation between the flows in site j and site h. This is given by, you take the flow in site j for the time period I is equal to 1 to n number of observations are available, and deduct the mean of the site j, mean of the flows at site j. Similarly, x h, this indicates at site h, but now we will reckon the time period k time steps ahead. As I showed, you have the site j here and site h here, and then what we are talking about is, if you are at this location, this h I plus k will be here. So, this is I, this is I plus k, and this is a k time steps ahead. Okay. So, that is what we do here. On the site h, you lag it by k time steps and then take this, and this is the mean of flows in h. This is standard deviation of the flows of site j, standard deviation of flows at site h, and because we are using lag k, this becomes n minus k. Please also refer to our earlier discussions on the autocorrelations etc., where we do the lagging, that is, we are talking about lag k autocorrelations etc. It is much similar to that, except that we are now talking about cross correlations at those lags. So, this is how we compute the lag k cross correlations. Now, this is an important input into the multivariate stochastic models. In the single variate stochastic models or the single site models, the lag k autocorrelations were important, and specifically the type of models that we saw, lag 1 autocorrelations were important. Whereas, in the multivariate stochastic models, not only the lag k autocorrelations on each of these sites, but also the lag k lag k cross correlations between the site j and the site h, between the flows at site j and flows at site h, they are important. So, let us see how we compute this now. We have two simultaneous sites, simultaneous observations on two sites. let us say this is site A and this is site B, and both of them belong to same hydrologic region or homogeneous hydrologic region, and you want to build cross correlations among these two. Now, these type of problems are also important in applications where we are talking about prediction in ungauged basins. You may want to use the little data that is available. By ungauged, we mean where the data is small or data is completely absent. You may want to use the data that is available in a nearby stream, build the correlation structure, build the dependence structure, and then use that dependence structure to generate the data at the location where data is negligibly small. So, we have for 19 years now annual rainfall at site A and annual rainfall at site B. Now, these are the data that are available. So, using this we will now look at how to develop the cross correlations at various lags. So, we are now talking about lag 1 cross correlation. So, we will see how to get the lag 1 cross correlation. Same thing can be done, same procedure can be adopted for obtaining different lags. Now, the mean values which are again in depth units millimeters at site A is this and at site B is this. Now, the lag 1 cross correlation at sites A and B using this expression now. Now, this is A and B and lag 1 correlation. So, k is equal to 1 is what I will put here. So, I write RAB, that is the lag 1 cross correlation between the flows at site A and site B, and this is lag 1, and this is the data on A and this is the data on B, one time step ahead. So, if we are looking at ith time step, you take the I plus 1th time step on the data on B, and this is the mean of flows at B, mean of flows at A, which are obtained here from the data, and this is a standard deviation at A and standard deviation at B. So, this is what we use and compute the lag 1 cross correlation between the flows at site A and the flows at site B. So, this is typically done using any of the spreadsheet programs. Typically, you use Microsoft Excel or any spreadsheet program that you are used to. This is the data on A, annual rainfall at A and annual rainfall at B, and then you have computed already the mean of A and mean of B. So, this is the data rainfall at both these locations. I am sorry I indicated it as flows, but these are in fact the rainfall at two locations. Just make that correction, these are not the flows. You are looking at a watershed here, and then there are two stations A and B, and we are interested in getting the cross correlations between the rainfall at A and rainfall at B. Even if they were flows, the procedure remains the same, but for this particular problem I am taking the rainfall at these two locations. So, this is the record available on the rainfall at A and this is rainfall at B. We have computed x bar A. So, simply take out x bar A from this. So, you constitute this series. Because we are talking about lag 1, we will take the second data for this. This is x A I minus x bar. So, this is corresponding to this value, that is 5496 minus the mean of that is this. Then 6934, the second value we take for site B, because when I is equal to 1 I am talking about the second value here, and that is what leads to 865. Then x A I minus x bar A, this is what I have to multiply, x A I minus x bar A into x B I plus 1 minus x bar B. So, from this I multiply to this and then get this particular value. Similarly, this multiply by this I get this value. Like this we compute this term now, and then we sum it and get the sum of all these values, and that is what gives you this term now. This summation is what we sum along this, and that we use. So, this sum comes out to be this number 3373079, that is the sum of this. Again, just understand that I will take I is equal to 1 and for I is equal to 1, I will use for rainfall at A the same value, and for rainfall at B I use the second value, because we are talking about lag 1 value here. Let us say we are talking about lag 4 value now. For this value I will take I is equal to 1, and next one I will take I is equal to 5. So, you are taking essentially I plus k. So, this is how you tabulate and then obtain the sum of that, and that sum is here in this particular case it is 3373079 for lag 1, and then you use this formula n minus 1, n is 19. So, and SA is the standard deviation at site A and standard deviation at site B, rainfall at site B, and then you get the lag 1 cross correlation as 0.164. So, this is how you get lag k cross correlations for varying k. Let us say this was lag 0 now, that means lag 0 cross correlation. It is simply the cross correlation between the two variables, in which case you can see from the formula that this will be again x b I itself minus x bar b. So, this is just the cross correlation between the two variables. So, we use typically the RAB, or in terms of your population notations it will be rho AB at various lags in our multivariate stochastic models. Now, we will start with multi-site Markov model. I discussed at the beginning of this lecture the Thomas Fearing model. Thomas Fearing model is the single site Markov model, and it is a single site one step Markov model in as much as we consider rho 1, that is lag 1 autocorrelation. Now, we use the single site Markov model and then start developing multi-site Markov model by adding the cross correlations. Now, in the single site Markov model we had only the autocorrelations, and we start with that and then start developing the cross correlations into that particular model. The single site Markov model or the Thomas Fearing model that we talked about earlier preserves the mean, the standard deviation and the lag 1 correlation, and therefore, the multi-site Markov model that we want to develop should preserve the mean at both the locations. Let us say you are talking about 2 locations, it should preserve the mean at both the locations, it should preserve the standard deviation or the variance at both the locations, it should preserve the lag 1 correlation at both the locations, and it should also preserve the cross correlation, because there is a cross correlation among these two. So, starting with the single site model, we now proceed to multi-site models, where not only the mean, standard deviation and lag 1 correlations of a particular site are preserved, but also the cross correlations, which indicate in fact the dependence of one site on the dependence of the variable on one side on the variable on the other side, these are also preserved. How do we do this? We will start with a case of only 2 sites first, and then we will generalize it. Let us say you have a watershed and you are interested in getting the generation on 2 sites, and these 2 sites are correlated. The flow, the random variables on these 2 sites typically will take the flows, the stream flows at these 2 sites are correlated, and therefore, we cannot assume them to be independent, and therefore, we cannot use the single site models for both of these. When you have 2 sites, that is the data on 2 sites, we will choose one of the sites to be a key site. Now, this procedure is explained in Han, I am using the same procedure. We will choose one of the sites as the key site. Remember, you want data generation on both the sites, and one of the sites has longer data and maybe the quality of the data is also better. We use this data, we use this particular station as the key site and generate using the single site model, we generate the data on the key site. Let us say I denote the key site as J, and the other site we call it as subordinate site. So, there is a key site j and the other one is the subordinate site to key site j. On the key site, we will generate using the single site models. So, using single site generation technique, we generate the data on the key site. How do we do that? This is your first order Markov model for single site. This is the non-stationary model. So, I will use this model with non-stationarity. Now, in this particular way of writing it, I is the year and j is the month within this year. So, we are generating it for several years now. So, this is year and this is month, j plus 1 is a month, and this is our Thomas Fearing model that we have used, and these are the standard normal deviates. We use this particular model either in stationary form or non-stationary form. We will start with the stationary form here, where on the site H you want to generate the values here. Okay. So, you will use this particular model and then generate for site H. This has to be t plus 1 if you are using time period t plus 1 and you are using the earlier value t, and this is the cross correlation between the site j and site H. Okay, just one second, I will do the correction correctly. Let me explain this correctly again. You are talking about the flow in site H in time period t. You are using the flows in time period in the station j in time period t. Okay. So, on the key site, which is the site j, here sequence of observation is generated for site j using single site generation technique. So, what we have done? We have identified the key site, which is the site j, use the single site model and generate the data. You use either the stationary model or the non-stationary model. So, at j you have already generated the data. Now, you move to the subordinate site. The subordinate site I am denoting it as H. Now, that is what we are doing now. So, this is your key site and this is what we denoted. I am sorry, it is not coming here. Okay, let me write it on a different sheet altogether, so that this point is not missed. We have two sites now for the watershed and we want to generate data on both the sites. Let us say this is the watershed and this is site number, we will call this as j, this is as H, and this is what we call it as a key site, and this is called as the subordinate site. Now, the key site we choose based on the length of the data. There is a longer length of data that is available on the key site, and therefore, we call it as a key site, and also the quality of the data is much better than that available at H. So, for the key site we simply use the single site model. We use single site model and generate the data on this, and then when we come to H, the subordinate site, we use the generated data on the key site, which is a single site, which is done using the single site model. We use that and then build the cross correlations and develop the model for this. So, this is what we are doing now. So, we are talking about generation on the site H, which is the subordinate site, because we are talking about only two sites now for time period t, and this is the mean of the flows at site H. This is RJH, which is the cross correlation at lag 0 between the flows at site J and the flows at site H. This is cross correlation at lag j. This is a standard deviation of flows at h, standard deviation at standard deviations of flows at j and so on. So, we are using the flows at j to generate the flows at h, as all other things essentially remain the same, except now the random terms that we are building here. This is a random term, ut is a random term, and these are known now, sh is the standard deviation and so on. When we put it in this form, this will preserve the mean, standard deviation and lag 1 correlations, and also the cross correlations, not the lag 1 correlations, it will also preserve the cross correlations. Let us see what are the properties of ut. Now, this I have indicated here for use on the key site j. So, on the key site j you just use it, except that the notations are different here, I is the year and j is the month within this year. So, this is a single site model, this single site model you use for the site j, and then using the observations on site j you generate on site h. Now, the ut, which is a standardized random variate, we do this to incorporate the serial correlation at site h, serial correlation or the autocorrelation. So, at site h you also want to build in the autocorrelations, lag 1 autocorrelation. So, the ut is defined as zeta x h t minus 1. So, at the site h you are doing it minus x bar h, this is the mean of that, divided by the standard deviation, plus T t is a standard normal standardized random variate. Remember, we are still not talking about normal variates, it is just a standardized random variate and root of 1 minus zeta square. Now, this is developed by Fairing in 1969 and this has been discussed in the textbook by Hahn. So, we will not go into the details of these, we will just see how to use these expressions. And the zeta is given as R h of 1, this is the serial correlation now. So, when I have only one subscript here, that indicates the serial correlation. Serial correlation at lag 1 at site h. Similarly, the serial correlation of at lag 1 at site j, and this is R j h 0, which is a cross correlation between the flows at site j and the flows at site h at lag 0, that is a cross correlation, and then we are taking a square of that R j h square at lag 0 divided by root of 1 minus R j h square. So, this is how you compute zeta, this is known, you can compute these and therefore, you compute zeta. Once you get zeta, you compute ut, where you will use T t as a standardized normal variate, standardized random variate, I am sorry, not normal. Now, with this now, we form the multi-site Markov model. Okay, just look at this now, we complete up to certain point now. So, starting with the first order Markov model, which was a single site model, we have now developed a two site model. For the two sites, what we do? We identify one of the sites as a key site and generate the data using a single site model for the key site. The other site, which is a subordinate site, we build the model by taking into account the cross correlations among the key site and the subordinate site. Where did we build the cross correlations? This is the term which has cross correlation R j h 0, it also appears here, but also in the term ut we have the lag 1 serial correlations. So, you are talking about both the cross correlations among these two sites as well as the serial correlation for the site for which you are generating it, and this is how the dependence on the other site has been brought into the Markov model. and as I mentioned in the term UT here, you have the lag 1 autocorrelations of both the site H as well as site J, and you also have the cross correlations between the site J and H. And this is how you build models for two sites. I mean what I mean by that is, when there is a cross correlation between the two sites, you will use this two site model to generate the data. Now, this can be extended to multiple sites. We will see how it is done in the next lecture. So, in today's lecture essentially we have started with the single site models and then went on to develop models for multiple sites. And the point that you must remember is that when typically these cases arise when there are several streams, let us say x1, x2, x3 etcetera. These are the flows on different streams, and you want to generate data simultaneously on the random variable x1, x2, x3 and so on. So, when you want to do this, if these can be assumed to be independent, then the single site models can be used. We have discussed the single sites earlier, single site models earlier. Those can be used. Typically, the Thomas Fearing model in its stationary form or non-stationary form can be used. However, when there is a dependence or the cross correlation exists, significant cross correlation exists between two or more of these random variables, then we go for multivariate stochastic models, where the cross correlations among several of these can be brought into the models. We have also seen the cross correlation at lag k between two stations, between the random variables at two stations. Let us say j and k, I am sorry, j and h, there are two stations, and then we are talking about cross correlations at a particular lag k. This is similar to what we do in the autocorrelations by lagging time, except that you are lagging time on the other station now. And we have seen in today's class how to compute the cross correlations at lag 1 through an example. The same procedure can be adopted to obtain the cross correlations at lag k, and these cross correlations at lag at different lags can be brought into our Thomas Fearing type of models. And specifically we have discussed today for two sites how do we generate data by incorporating the cross correlations. Initially we identify one of them as the key station, simply use the single site model for that key station, and then go to the second station which is a subordinate station, and then build the cross correlations between this key station and the subordinate station, the variables at these two places, and then build the Markov model. We will take this discussion further and then look at how we generalize this for multivariable generation. So, thank you for your attention. We will continue the discussion in the next class.